All right, good morning and happy Friday. It's September 15th, and I'm planning on doing the LeetCode Daily Challenge for today. So here we go, share my screen, the 15th. Minimum cost to connect all points. Manhattan distance. Okay, so this is a minimum spanning tree then, right? Minimum, right? MST is a minimum spanning tree, 6:27 a.m. So we can do this in two different ways, right? You can do union find, which is Kruskal's algorithm. Kruskal's, or we can do the greedy, right? Similar to Dijkstra. Oh, what's that one called? I forget now. So we use like a minimum priority queue, right? Min PQ. Forget which one this one's called. So if you use the minimum priority queue, it's similar to Dijkstra. STRA. All right, so here we would order the edges by cost and iteratively add edges which do not create a cycle. I'm surprised I forget what this one's called now. I guess it's been a while. It's some other way of constructing a minimum spanning tree. Maybe it'll come to me. So let's do the union find first, and then question. What is this one called? What is this algorithm called? I forget. Maybe it'll come back to me. Okay, anyhow, we'll do the union find first. 629. So implementation for union find is ordering the edges. Well, the cost is the Manhattan distance. Okay, so let's see if this works. There's 1,000 points. There'll be a million edges or so. Vertices, right? The amount of vertices was 1,000. So then the edges would be the pairs. So the first of the pair, there's 1,000 choices. The second of the pair, there's 999 choices. So it's like a million or so. So it's questionable if that'll TLE, right? So the question, will considering all pairs result in TLE? And that really matters. It really depends on the online judge. I found like you can do about a million operations or so on LeetCode, so it's like kind of borderline. But we'll see what happens. We'll just try it, right? So all our edges will use these guys, and then for each point, we can create an edge from the endpoints. Suppose we can just reference the array for our edges so we don't have to be redundant. So for each ith index and it'll be the cardinality of our vertices array range n or jn range I plus 1 until n e dot append. These are all our edges. Be ith value and the jth value has a tuple. And then we'll order the edges by the Manhattan distance. So let F be our Manhattan distance. Let's take us in the ij for each edge endpoint to the array A, and then returns the absolute difference between a sub I sub 0 and a sub j sub 0 right? So that's the difference in the x coordinate plus the absolute difference in the y coordinate. Oops. So 0, 0, and 2, 2 would be 4 away, right? 0, 0, and 2, 2, 1, 2, 3, 4, right? Okay. So there's our function for Manhattan distance. And then actually the edges we can order by that then. So we'll order it by distance. Okay, and then we'll do the union and find. So def find, we functional, def find is the parent representative of each set. So P, let's see, we'll keep track of, right, yeah, the indices. I for I in range in parent representatives of induced joint sets. Let's see. Parent representatives, representatives of n disjoint sets. If p sub x is not equal to x, that is, x is not the parent, then we'll go find it and use path compression. So p sub x equals find p sub x. Parent p sub x. Okay, and then union, we'll take A and B, find the parent representatives of those. And then if they're different, then we'll union them. Otherwise, if they're not, then we will not. P sub A does not equal, oops, if A does not equal B, right? Parents aren't equal. They'll return true, none of those return false. Let's do this, return false in this case, return true here, and then the parent of A. No, those are X. Choice. I was in to think, like, I haven't written this in a while, but do I want to check the parent of A versus the parent of B, or X? We don't want to return X, right? It's the same thing, right? P sub A and P sub B, I'm pretty sure is the same thing, right? As this thing returns, X is the parent of itself. Okay, I think that looks right. Okay, so then for all the edges sorted, for cost here, let's call this thing cost. It's consistent, right? Cost is this function, or dist, how about distance? Is this Manhattan distance? Minimum distance. Oh, here we call it cost. Sorry, whatever. We'll call it cost. For cost, I, J, and sorted edges, right? Yeah. Okay, so if union IJ, then we'll increment the cost, right? The total. Total. Okay, something like that. Let's see what happens. 629 to 638. Let's okay, so start debugging. Debugging. 78. Holy cow. Okay. Percentages in disjoint size. Okay, let's just do some debug prints here real quick. So union of IJ failed. Okay, let's see what happens. Actually, let's print the edges too. Right. Oops. Cost. Oops. Okay. Okay, let's see what happens here. Okay, so the cost is 3 from 1 to 3. 1, 2, 3. What? Oh, 0, 1, 2, 3 is this guy. How's that 3 away? 1, oh, 1 and 3. Okay, I see. Okay. Yeah, 2, 2. Okay, 2, 2, and 5, 2. Okay, that makes sense. Okay, these two are 3 away. Okay. That makes sense. Okay, and then 0, 1 is 4. Okay, so that one would be part of it. 3 plus 4 is 7. Okay, 3, 4, 0, 1, 2, 3, 4, 5, 2, and 7, 0. Okay, that would be included in it. Yeah. So 4, 3, and 4. Okay, that's 11. And now all we need is just one more. That's the least. This guy goes, is this 10, 3? So 1, and then 8. So that should cost 9. 6. So what's going on here? 2, 3, 4. 0, 0, 0, 1, 2. Wait a sec. 0, 3 should not be right because that would create a. Oh, did I have this wrong then? Does this matter? The parents are the same. Maybe I should set this guy to parent to that guy. Okay, so that is a typo then. Okay, let's see how this works. So parents Still wrong. Okay, well, a little bit better. Okay, so we take the 3, take the 4, 2, 3, 4. We take the 4, 0, 1, 2, 3, 0, 0, and 5, 2. That would create a cycle though. Great choice. Union find doesn't seem to be working at all. Wait, what am I doing here? This is good to practice because I haven't. This is right for the cost. So then 9 from 0, 1, 2, 3, 4. Yes, that's right. 9 for this guy. What the heck is happening here? Okay, so this is piece of X, and it's the same thing though, right? Piece of A equals B. No, it's not the same thing. Okay. Doesn't, okay. Yeah, so that is a slight typo here. We do want to return piece of X. This part doesn't matter though, right? Because that should be the same thing, right? Wonder. Oops. Okay, so returning the X is not right. Yeah, because we're using path compression. That makes sense. Okay. So we do want it to be the piece of X, but then this is piece of X, right? So that doesn't really matter here. Might as well write it a little bit more consistently. Parent of this guy equals the parent of that guy. As long as we're returning piece of X from find, then it should be okay, right? The path compression was off until I did that. Okay. All right, minor failure in path compression. So 644. It's about 6 minutes for debugging, which is super costly. All right, so if I'm going to be a participant in the contest, I need to be able to be able to write this a little bit more faster, right, and accurately. Okay, well, heading in that direction slowly. Slow and steady wins the race. Okay, so it looks like I saw this about a year and a half ago. And that's accepted. Okay, so 645 took about 18 minutes. 18 minutes for the game plan plus implementation. Python 3, which is accepted. Yay. Okay, now the other question is, what is this one called? The other way of creating a minimum spanning tree is in a priority queue. I know I've seen it before, but it's been a while. Here, I'll go look. I'm just gonna look at the name of it, not, and I know what it does, right? But I forget the name of it. Prims, yeah, Prims. That's what, okay, Prims. This one's called Prims, right? So I implemented Criscalls using union find. That's implemented here. All right, so that took 18 minutes. So let's do Prims. So this is construct minimum spanning tree via Kruskals algorithm using union find. So this one's similar to Dijkstra in that we will keep track of the frontier, right? Prim's algorithm considers all edges. And what's interesting is you can start at a random vertex. Yes, then we consider all edges which cross the frontier. The frontier being what has been seen and already part of the MST compared to what's not part of the MST. Right, so that's the plan. And we use a minimum priority queue for all those edges which cross the frontier so we can cherry pick best. Okay, so we'll start at source index 1 about, and then I'm going to keep track of what's been seen. Seen is a set. Okay, so for every vertex in the set, we say, okay, here's the edges that cross the frontier, which are potential candidates to choose next. You. It will be a heap. Let's do this. Start will be, it could be random, but it doesn't matter. All right, we can just use 0. We have something in the queue to consider. Okay. I think that works. Turn T, total. Well, actually, before I do this, let me go back to this other guy here real quick and clean it up real quick. So this one, right at the end, we can just make this the accumulated sum. Cost for cost I, J, and sorted E if union IJ, right? So we don't need all that. I think that works. Might as well make it more concise, right? More Pythonic. Okay, that's cool. So then, back to Prim's algorithm using constructing MST using Dijkstra's type algorithm. So our edge that we have currently would be keep off from the queue by index. And we do need to consider all the edges still, right? So edges and their cost. So I still want this stuff, right? This is all useful. So here's our edges, which are all pairs of the array A. I want to do this. So yeah, edges out. So you want an adjacency list, right? And so from this vertex, just say and go to these other vertices. the value is not in scene for j in range n. If j is not in scene, then it's a valid candidate for pushing onto the heap. Let's see, so we're going to keep track of the cost then. And so it's a minimum priority queue, so the minimum cost. So cost will be 0. Start. Cost will be this function taking okay, so there's our function that is the cost for us. Okay, so scene will be a set, and then we'll mark it as scene after we consume it as part of the MST. Right, so scene.add I. And for everything not in scene, actually, instead of doing scene, but maybe just do need. And then whatever. Okay, we can consider that maybe as an optimization. Okay. I'll mark this as a atomic operation on one line. Okay. And then Q dot or heap push onto the queue, the cost going from I to J. Right. Works on cost of I. T plus equals cost. So starting here, what's the minimum cost of all these guys? All right, well, we're going to push them all onto the queue. This one should win. And from this guy, it's not been seen. This guy's seen. It's the minimum of each. This guy, and take that guy. Okay, so I think that looks all right. Let's see what happens. 655. Uh-oh. These are way off. 116? Oh, okay, hold on. I don't want this. While the length of scene is less than n. All right, we want to just see n. Put better. 41 is not right. 18 is correct. It's almost right. Okay, so start debugging 655. Debugging. When did I start? I think I started at 645 ish, 645 ish. Okay. So what's going on here then? Scene. Scene. I guess to do some prints. Is not in scene. Right, it crosses the frontier. Wait. Yeah, I don't know. Let's print what's going on. Good old printf debugging. Okay, like value is cost. Yes. Okay. Mm, let's just reduce this to the first one. So the second one is correct, so that's nice, but first one's wrong. That'd be plus 5 minutes for each bug. Oops. Yeah. Prim's algorithm is not working. Total is 4. Okay, so that looks right. Then 3, that's right. Then 4. Then it should be 9. So 18. So here's where it's going wrong. So that's correct. That's correct. That's correct. This is wrong. Cost is 7. A 0, 1, 2, 3, 5, 2. 5, 2 should already have been seen though. Yeah, it's okay. This is a lazy queue then. If it's seen, continue. Okay, small bug, but that makes a big difference. Okay, that looks good. 655 to 659. Debugging. Submit. Okay, that looks good. So Prim's algorithm, 14 minutes. Oops. 14 minutes. Prims, MST, and then it took about 18 minutes for first calls union fine MST. Okay, so that was fun. It was good practice to write the code and debug it a little bit. So here it's important to return the parent representative of the set, not exit cell. Right here doesn't matter what we compare. Here doesn't really matter so much, but this does matter, right? You need to return the parent representative of the set. So path compression is pretty easy to make simple mistakes. And similarly here, this is a lazy queue, like a lazy priority queue. That is, when we add new stuff, we aren't checking to see if the queue has some stale information. So it's important to skip past the stale information because that would cause a loop, right? We don't want to loop in our MST cycle, right? Okay. So the other thing I was thinking is instead of keeping track of what's been seen, we can use inversion and track what we need, right? So each ith value for I in range n is what we need, while we still have some needs. If I is not in need, continue. Okay, and then J is in need, then we'll add it. Okay, so this is the opposite of seen. That's what we need. Oh, get a comma. Well, no, I forgot a keyword. And range in. And the Cardinalian for AA. Right, so each index. Oh, seen need dot remove. Right, so it's backwards. Okay, that looks good. So it's a little bit different way of thinking. So here's where it was somewhat inefficient, right? So if we go through every single J and then we could just basically skip past all the ones that are seen. Whereas here, we're only focusing on need. Oh, here, let's do this for J in need, right? Here we go. If I and let's just keep it consistent, right? If we need I, And we need J. Take it and remove it from what we need. Okay, that looks good. Let's see what we came up with previously, and then I'll go take a break and walk my kids to the bus stop. Oh, cool. Yeah, that dude came up with both prims. Okay, Crisco. It's holy cow, this is ugly. Okay, I mean that can be shrunken up. Actually, path compression. We can shrink that up. Okay. Oh, that's cool. We have the weight. That's fun. Okay. Yeah, so definitely clean this up a little bit. Holy cow. Yeah. JavaScript doesn't have priority queue, so I made one myself. Holy cow. Okay. This is really verbose. Yeah, so we can tweak this up and make a lot of improvements. So that's cool. This is only a year ago that I wrote these, and I feel like I've already made a significant improvement. Look at this. Like my prims algorithm is super tiny compared to a couple years ago. And the less code that we write, the less chances for bugs and failures, right? Because we're all imperfect human beings trying to write somewhat good enough code that works sufficiently. So it's cool to make some of these optimizations where we use need as the inversion of seen. And then similarly, like using Pythonic short abstractions, there's just less code to look at, like less to keep track of, and that's a good thing. Okay, so well, it's 7:04. I suppose I can start making some of these changes when we get to the bus stop till 7:25. So we still have 20 minutes. Yeah, might as well. There's some updates here. So here's Chris Call's algorithm. And if y'all have any questions about any of these things, let me know. And I basically built up an algorithmic toolbox since 2017. So it took me like 6 years, but a lot of my stuff in my GitHub repository I still refer to. Like Algorithms Illuminated by Tim Roughgarden is super cool. This is kind of like this is a subset of this stuff. And yeah, I mean, it takes some time too, right? It's not like super straightforward or fast to understand some of these algorithms. And the algorithm itself is an intimidating word. I'd prefer recipe, right? So an algorithm is basically a recipe for getting something done. Criscal's algorithm. Wait, hold on. Okay, so this one's Criscal's. This guy we can clean up a little bit. Sets, edges. Okay, that looks good. And then this guy. Int is only used once though, so I'm gonna get rid of this guy here. Then, or am I using int more than once? Yeah, I'm using it a couple times here, so that makes sense to have it there, but here it doesn't really make sense. It's pretty awesome how short this can be. Okay, so prim's algorithm. Yeah, so prim went from this giant thing that I wrote like a year ago, year and a half ago, to something nice and short. Awesome. Yeah, that's freaking cool. Push it up there. Let it be a lazy. Okay, cool. Well, let's do this. Yeah, do C++, whatever. All right. Chris calls, MST. Oops. via union find 707. C++ is verbose, so let's see what happens. Come on. Okay, so Q, here to Q. Is a maximum one, right? So actually we're gonna have a pair with constant index. Gonna be a pair of pairs. Pairs. Then custom comparator. So the comparator operator for a priority queue is kind of weird in that it's like backwards, right? So if we want it to be a minimum priority queue, we have to compare the cost, which is the first of the pair, in reverse order. It's a little strange, but I'm pretty sure that's how that's done. Okay, and then so there's our queue. Oh, oops, I'm doing MS. I'm doing this is actually prems. Here, we'll do Chris calls next, but I just started doing prems. Queue constructor. Let's look at it. I'm gonna rotate this very often. Priority queue CTOR. What's the constructor look like? Custom comparator. Yeah, we can't just pass an initial value. So let's just do this. Q Q Q dot push 0. This could be a random vertex, but we're just going to use 0, whatever. And then let's do this using a set as an owner set integers we need. That need for I is 0, I is let's say that size. I. Okay. So cost for each ith value is q dot top. Q dot top. If need I not equal need I. So we do need I. Okay. Need move I and then t plus equals the cost. T of our total we're turning the into. Okay, so for each jth need, say the cost. Capture a and reference turn a sub I sub 0. The absolute difference between this guy and the absolute difference between that guy. I don't know if we just want to call this thing cos. Yeah, no, that's okay. Q dot push the pair cost of the jth value. Okay, let's see what happens here. 7F7 to 713. Uh-oh. Q dot. Really? There's no push? Is it add or? Yeah, hold on. Q, priority Q. Where's the other functions of the priority Q? Push. Oh, 0. Okay, that makes sense. Okay, it's a pair. The cost is 0 to go to 0. Okay. Base. Oh, okay. Looks good. It's 7:14, about 7 minutes for implementation, and C++, which is accepted. Yay. Okay, so this is way better, I think, again, than my previous C++ solution. Yeah, this is junk. Okay, nice to know that there's still significant improvement being done here, right? I mean, that's like half the size. Okay, that's awesome. Okay. While I'm here, I might as well just do the crisscross here real quick in C++, and then I'll come back from my kids to the bus stop and I'll do the other ones, find their languages. Okay, so we don't need a, for crisscross, we don't need any of that stuff. We do need to keep, we don't need to keep track of what's seen this way. All right, use the parent representatives in disjoint sets to track what's been seen. Okay, parent representatives in the set will be key. There's the Cardinality for A. Parent should be this guy. I go to, actually we'll assign these 0 valued monotonically increasing for each index. Okay, and then a Q or anything, we'll get rid of all this stuff. Okay, we need a find function, which will capture itself in its own lambda to be invoked recursively. Find will return the parent representative of each element or index using path compression. So fun, it is fun. Undefined. Capture itself in your own lambda. Return piece of x equals find piece of x. Piece of x equals x. X, otherwise find it. Okay. And then union. Capture all this stuff and reference. A is find A, B is find B. If A equals B, return false, otherwise return true. After we arbitrarily set parent of A to B. So put some comments in here. Parent representatives in disjoint sets. Arbitrary choice. Right, that is, we can set the parent of A to B or the parent of B to A. It doesn't really matter. Arbitrary choice. Okay. Actually, we want to call this thing, we'll just call it join instead of union, since union is a keyword or a keyword in C++. Okay, and then yeah, we need the list of edges as well. So let's do this using pairs, and using pairs as a vector of pair. Edges will be pairs. Oops. Pairs, edges. Okay, and then to 4, 0, so it's then I. Okay, so I plus 1. So these are all IJ pairs. E dot push back. Just in place back. So move the R value reference. Here. Cost of I to J. Oops. It needs to be a triple actually. I J. 8. Sorted by edge weight. Triple. Tuple. 3 ends. Edge weight IJ for each edge. So there's tuples. Okay, so then for cost of IJ edge and edges. If union IJ, oops, join T plus equals cost. Doesn't matter. Right, okay. So as long as the edges are sorted, sort it right here. How about with the edges, sort them. Oh, P. Yoda. What's the number of P? Oh, there's a dot, comma. Okay. This back. Really? Oh, I need to call that a tuple. Okay, hold on. Really? Tuple for an oh, triples. Triples. Okay. Okay, that was good. 722. All right, that's accepted. Oh, I don't know when I started on this one, but 722 is accepted. Okay, so anyhow, this is it's a better solution than what I previously came up with as well, right? So let's see, hold on. This is Rams. Rams is, oh, I just already copied and pasted that. Okay. So it's already there. And then yeah, it's this guy that I'll replace. Holy cow, this thing is huge. edges. Okay. So it's, yeah, it's just very verbose. Okay. Let's grab this guy. This is a better solution than I came up with previously, year and a half ago here. So basically replace that whole thing with this linear thing. At least it fits in one screen. Okay. Yeah, so this is a work in progress, but I'm gonna submit this now. So I'll update Kotlin, JavaScript. Like this Python 3 is looking sharp. C++ is looking sharp. Some of these other ones are kind of verbose still. Oh, this is looking good. I'm totally stoked to see this one. And then similarly, this one's quite a bit smaller. Like these things are like half the size they used to be. So it's super cool. All right, we'll catch y'all later.